Hey everybody, it's Todd Francis, and I'm doing this lecture. This is going to finish up Chapter 8, which is where we ended right before spring break. The first part of Chapter 8, we focused on two things. We focused on the arrangement of the electrons in the atom. We talked about electron configurations and orbital diagrams. When you go back through there, review the things. One of the major parts with the electron arrangements is the filling order. And that was one of the things I emphasized with it, whether you're doing configurations or orbital diagrams. The second part of Chapter 8 focuses on the periodic table. So we're going to go a little history here at the start. Dmitry Mendeleev, when he put together the first table in 1869, as you can see here, used atomic mass. That was what was available to him. In the next slide, this is actually his first table. But what's interesting about this table, again, you can see 8 groups, and you follow the numbers. Like I said, they're all atomic masses. But what was interesting is he left some gaps here at 44, 68, and 72. Mendeleev, when he put together his table, noted that elements within the same group had similar chemical and physical properties. But in some cases, here's titanium, element 40, atomic mass 48. It did not have the same properties as boron, aluminum, yttrium, indium, but instead fit more with calcium, silicon, titanium, zirconium. So Mendeleev put together these gaps, and what was interesting, he actually used the properties of the elements in the group to predict the properties of the new elements. So for these 3 elements, he predicted obviously their atomic mass, but he also went through melting points, boiling points, density, compounds that they would form with different elements. Those 3 elements, respectively, were gallium, scandium, and germanium. And when those 3 elements were discovered, the properties of those 3 elements matched what Mendeleev had predicted. And that gave scientists the knowledge, okay, hey, our table that Mendeleev put together is what we want to follow. Now, over the years, again, Mendeleev was 1869. Our modern table, the one that you see on the inside cover of your textbook, actually started in 1913. Scientists by the name of Henry Moseley used, and you can see the statement there, using X-ray spectroscopy to determine the atomic numbers for the elements. Think about what we know in 1913. We know about electrons. We know about the nucleus in the atom and the positive charge. So what Moseley was actually doing was determining what we call this nuclear charge for the atom. And look with the note. He noted that it increased by 1 as he went from element to element. Our modern table is put together such as that. And again, this is just an example of a modern table, very similar to what you see on the inside cover of your book. And this is one, like I said, we want to follow with that. The idea of the periodic law does go to Mendeleev's, but now with a slight change. Elements are arranged by atomic number. So again, each of these, we're looking at the numbers above each of the element symbols. The physical and chemical properties will vary based on the groups that they're in. They vary periodically, so that we see that. So we're going to look at 3 particular properties: atomic radius, ionization energy, and electron affinity. As you look at these 3 properties, I want you to focus on 2 things. 1, the definition. What does each one define? And 2, not the exact numbers, but instead, what is the trend as you go within each group and within each period? That's going to be important. Atomic radius, you see the definition here, nothing much, the radial distribution function of the outer shell. Quite simply what that is, that's the measurement, the distance from the nucleus to the outermost energy level. The trends, like I said, very important. Within each group, the atomic radius increases with the period number. One of the things we mentioned at the end of Chapter 7 was that each successive energy level was larger than the previous. That's what we're seeing here with this trend. As you add energy levels, which you see with the period number, you're getting farther and farther from the nucleus. Also, and that's what it states there, within each period, now the radius decreases. Our atom gets smaller. And here, one of the things they talk about is there's an attraction. There's an attraction between the electrons and the protons. And that attraction makes the atom grow smaller with that. The next couple of slides give you some data that you can use. I don't focus, and I don't want you to focus on exact numbers. What I want you to focus on is the trends. What do you see within each group and within each period? The same with ionization energy. Remember, the formation of the ion involves either the gain or loss of an electron. So ionization energy, the energy needed to remove a valence electron. So those electrons that are in the outermost energy level, okay, that's what we're removing. And again, we're going to focus on trends. We're not going to look at exact numbers. The numbers we can always look up, okay? Within a group, ionization energy decreases. So again, if we're talking about electrons in the outermost energy level, as you go down the group, the energy level, that outermost energy level, is farther and farther from the nucleus. The electron's easier to remove. As you go across the period, since there's more traction between the electrons and the protons, it becomes more difficult to remove an electron as you go across. And again, you've got a couple charts here that you can use to note that. And I'm going to skip ahead here. And again, we've got numbers, but I don't focus too much on those. Electron affinity, which is the final trend. If ionization energy is for the removal of an electron, electron affinity is for the addition of an electron. And here's one of the things that I want you to take out of this. The larger that negative value, the larger the energy change, the more stable the anion. So what we see for an electron affinity when we go to particular groups is here's the halogens, the group 7 elements. They all have the greatest electron affinity. They all form the most stable ions. Here's the group 1, the alkali metals. They form the least stable ions. Okay, so the greater that energy change, the greater the more stable the ion. And again, you've got this chart of tables that you can look up, and it justifies the numbers. The last part of this the chapter looks at the main groups, and I'll let you go through each of these, whether it be hydrogen, the alkali metals, so you'll note the names. What you'll see in parentheses is the valence shell configuration. So just substitute in 1, 2, 3, 4 for the value of N that you see here. Now you don't go too in-depth into each of these, but I want to focus on some highlights. One of the major highlights we'll talk about here first is in group 4A, which is carbon. Carbon's a really interesting element because there's an entire branch of chemistry devoted exclusively to carbon, and that's organic chemistry. Carbon also exists as one of 3 allotropes. You're familiar with diamond. If you're writing with a pencil, you know you have graphite. And then there is Buckminster fullerene, C60. Group 5, as we get into here. Group 6, now we've got oxygen in this group. Group 7 is also very interesting, the halogens. And the reason for the interest is that this, as it says there, this is the one group where you have all 3 physical states. So you got fluorine and chlorine that exist as a gas, bromine as a liquid, and iodine as a solid. This is the only group in the periodic table where you see those 3 things. And again, you've got the examples of those. And then finally, the noble gases. This is our far right column. They have that full valence shell. And again, you see that with that. Okay, so this was just kind of a quick review of the final part of Chapter 8. If you have any questions, again, please contact me. Take care.